Okay, so good morning everyone. Um, so we will continue our discussion of this problem of division. So as we saw last time, we want to prove that division is in NC1. Okay. So what we showed is that last time what we showed is that these two problems, division and powering, they are equivalent modulo NC1 reductions. And we also saw that if we are doing division by small numbers, that is, let us say if I am dividing by m, where m is less than n, then I can find quotient, remainder, all those things in NC1. Okay, so division by small numbers is easy to do. And then we saw this result that if I have a and also the other thing that we observed last time is that this other problem, iterated product. Okay, so what we will show is that, so ultimately what our goal is to show is that iterated product can be done in NC1, because observe that powering is nothing but a special case of iterated product. Okay, so that is the goal that we want to solve, that iterated product is in NC1. So what we will start by showing today is that we will show that if I can compute iterated product, if I want to compute iterated product modulo some prime power, okay, that I can do in NC1. So this is the first thing. So now to prove this, we will be actually working in this multiplicative group. Okay, so let me first state some facts from number theory. So some of these are easy to see, and maybe I will discuss them briefly, or you can also work them out by yourself when you go back. But there are a couple of points which are actually not so trivial. Okay, they need actually more heavy duty number theory to prove them, and we will actually just take them as facts and move forward. If you are interested, you can of course go back and look up the proofs. Okay, so what are the things that we want? So has anyone here done a course on number theory? No one? Which course?
681 computational number theory and algorithm.
Okay, so then you might know some of these things. Okay, yeah. Okay, so the notation that we follow is that, okay, so Z star n is the multiplicative subgroup of the ring Z mod nz, okay, consisting of exactly those elements that are co-prime to n. Okay. So Z star n is the multiplicative subgroup of the ring Z mod nz. So what is the ring Z mod? So what is a ring? So a ring is basically a set where you have both addition and multiplication, and so it is a group with respect to addition, and it is just closed under multiplication. Okay, it need not have multiplicative inverses. Okay, so here if we do addition and subtraction, if we do addition and multiplication in this set 0 up to n minus 1, and the computations are modulo n, then this actually forms a ring. This is something that is very basic, we know. Now look at all the elements in this ring that are co-prime to n. Okay, one can actually prove that it is actually multiplicative subgroup. Okay, so and with respect to multiplication, this set will have inverses as well. Okay. So, this is something that is again easy to prove. I will again I will leave the proof to as an exercise, but you can try this out if you haven't seen this earlier. So, now we will try to characterize this. Okay. So, okay, for odd prime p z star p to the power l is cyclic. Okay, where l is a positive integer. Okay, what does it mean? It means that it is not just a group, but it's a cyclic group. That is, it has a single generator. It can be generated by a single element, and we can also have the size of this. So, can anyone say what is the size of this? What is the order of this group? Yeah, so that also can be proven, that the number of elements, so the total number of elements in this ring is n. Okay, so the total number of elements is p to the power l, but the number of elements that are co-prime are only p to the power l minus p to the power l minus 1. Again, this is something that you can check, you can verify. I will just leave all of these things as an exercise. Okay. Now, this is actually something that is not easy to prove, that the group is cyclic. So, this multiplicative group is cyclic. Okay. So, showing that is cyclic is something that is quite non-trivial, and if you are interested, you can look up the proof when you go back, but we will not be proving this. So, I will assume that I will assume this as a fact. So, there is no reason why this group has to be cyclic. I mean, it can be anything, but when P is a cyclic group means it has a single generator. So, the elements can be written as, so there is a element, okay. So, cyclic means that a group, let me give it a name, G is cyclic if there exists an element G in G such that all elements of G are okay. So, here of course I am assuming that the operation is multiplication, that is why it is G to the power I for some I. Okay. So, now what happens for 2 when P is the prime 2? So, when P is 2, okay, for k less than or equal to 2, the same result holds, that is Z star 2 to the power k is cyclic and has order 2 to the power k minus 2 to the power k minus 1, and this is actually very trivial to see, because what is, so when k equal to 1, what is the group? It is just identity, it has a single element, right? So, when k is equal to 1, 2 to the power 1 is 2. So, it is the all the elements between 1. So, basically the elements in Z mod 2 are 0 and 1. So, 0 is not there in the multiplicative group, 0 does not have an inverse. Okay. So, therefore, the only element is 1, which is itself. When I take k equal to 2, then the elements are 1 and 2. Okay. And it is basically, yeah, so 2 is the, huh? 2 square is 4, so it will have,
The multiplicative group will be 1 and 6.
1 and 3, correct. So 2 is not there because so in both cases it's fine. Now what happens for higher powers of 2? For k greater than or equal to 3, z star 2 to the power k has 2 generators, okay, 5 and minus 1. So minus 1 is nothing but 2 to the power k minus 1. So I can also write this as 2 to the power k minus 1, and for all x in z star 2 to the power k, we have x can be written as a combination of these two. So x can be written as 5 to the power a times minus 1 to the power b, where a is between 0 and 2 to the power L minus 2, and b is between 0 and 1. So essentially what we are saying is that for k greater than or equal to 3, this group has 2 generators, 5 and minus 1, and every element can be written as, so in terms of 5 and minus 1, so 5 to the power a and 1 minus 1 to the power b, where a is between 0 and 2 to the power L minus 2 minus 1, and b is 0 1. So now you can see what is the size of this group. So the size of this group is, can you tell me what the size is? So what are all the elements that can be generated? So actually all these elements will be distinct for all. So here I have 2 to the power L minus 2 different values of a and 2 values of b. So it is 2 to the power L minus 1. Okay. So this is actually, so you can actually see what this group is, right? So if you look at let's say any k, so let's say if I take k equal to 5, so 2 to the power 5 is 32. So what are all the elements in Z mod 32 that are co-prime to 32? Okay. What are all the elements? All the odd numbers from 1 to 31. So 1, 3, 5, 7. So it's easy to see that it has 2 to the power. So it has exactly half that many. Okay. So it has 2 to the power 4 many elements. And now it needs some work to show that every odd number between 1 and 31 can be generated as 5 to the power a and minus 1 to the power. Huh? K. Yes, it is k here. Sorry. Okay. So this is all I think that we would require from number theory. Yeah. So as I said, some of these things are quite easy to see. In fact, you can also try proving this, that every element in Z star 2 to the power k can be generated, generated in this form. This one is a little bit more non-trivial, to show that every element in Z star p to the power L can be generated by a single element. It has a single generator, but the other things are easy to see. Okay, so any questions? So let's move forward. So now let's come back to the theorem that we want to compute this product modulo p to the power n. So what we will do is, first we will do some pre-computation. Okay, so we know that well, these are log space uniform circuit. So I know what n is. So given n, I can do some pre-computation, and p to the power l is small. So basically I can also assume that I know p to the power l, because I can do this in parallel for each and every p to the power l, okay, for each and every number that is less than n. So n is not large, n is small. So this I can use to do my pre-computation. So we'll do some pre-computation in log space to begin with. So what do we do? So first, what do we do, that for each prime power less than n, find a generator G for Z star p to the power l. Well, if p is odd prime, and if p is even and l is greater than 3, then we know what the generators are. Okay, so you can assume here that p is an odd prime over here. Find the generator, and yeah, okay. So if so why can we do this? How can we find a generator? So basically what we can do is, for each number, okay, so for each number that is less than n, I can just first of all compute the factors, and I can, by computing the factors, I know whether it is of the form p to the power l or not. So it is of, if it is of the form p to the power l, then what I do is that I will just look for every element that is less than p to the power l, and I will see that if that acts as the generator. So basically if I keep on multiplying that number, do I get all numbers that are co-prime to p to the power l, okay. So it's in a series of some nested loops, 2-3 nested loops, I'll be able to check this. Next what we do is that, given we have this, we will compute two things. So first we will compute all powers of G up to p to the power l minus. So again, so for the rest of the proof, so basically this proof will have two cases. Case 1 is when I have a single generator, okay, that is when either p is a odd prime or p is equal to 2 and k is less than or equal to 2, and the second case is when I have p equal to 2 and k greater than or equal to 3, in which case I have two generators. So for the rest of the proof, I will just, without, well, not without loss of generality, but I will just assume that I am only looking at case 1. I will only be showing it for the case when p is a odd prime. The other case when there are two generators is actually analogous. You can go back and actually, if you just work it out, you should be able to get it. Okay. So let's look at only this case. And then we will also okay, for each x between 1 and p to the power l, relatively prime to P write x as being congruent to g to the power I mod p to the power L, and okay, let's say that I output this I. So essentially what I am trying to say here is that, so in these 2 points, so this is what is called as the discrete logarithm of an element. Okay, so basically for every element that is there in the group, okay, I can write it as a power of the generator. Okay, so I am finding out what is the power of the generator. So basically for each power I am finding out what is the corresponding element, and here given an element I am finding out what is the corresponding power. So both these terms. Okay, so given an I can, if I have all of this pre-computed, I know what g to the power I is, and given an element x, I know what is the I such that x is congruent to g to the power I. Okay, so this is basically a table that I will keep, and I do this and I save this for each and every prime power L that is less than n. Okay, so all these things are pre-computed, and note that in none of these places I have used x. So the only thing that this depends on is n. Okay, so now we come to the circuit. What do we do? Okay, so for each x we will do the following in parallel. So for all xi in parallel, okay, so actually I can write this as 1. For all xi in parallel, we compute the largest power ji of p such that p raised to the power ji divides xi. So essentially what is the largest power ji such that it divides xi. So basically p to the power ji will divide xi, but p to the power ji plus 1 will not divide xi. So we compute this in parallel. Again we can do this by just repeated, just by dividing it by p at every step. So p is a small number. Next, and we set the following. So we will set yi as xi by xi mod actually I don't even need xi over here, so I can actually do this for xi mod p to the power L. Okay, so find the largest power of p that divides xi mod p to the power L. P is some prime that is given as input. So if you look at the theorem, it says that you are given x1 to xn and you are given a prime power p, some p to the power L, and you have to compute the product modulo p to the power L. Yeah, you can just divide it and you can calculate. So So again the prime power I think is less than n, right? Yeah, so prime power is less than n. So that is why you can actually factor it in log n steps. So I will compute the quotient. So xi mod p to the power l divided by p to the power ji. Okay, so why is this quotient? Next what I do is I will compute the sum of all these ji's. So compute j to be sigma ji I equal to 1 to n. So now what do we have? So therefore product of xi mod p to the power l is nothing but, so the product of these xi's mod p to the power l is nothing but product of yi times p to the power ji mod p to the power l, right? So basically I am factoring each xi mod p to the power l over here. So I can write this as product. Now I have this as product of all the ji. So what will this be? So I going from 1 to n. So this I have j as the sum of all the ji's. So once I do this for all the yi's, what I will get is that I can actually take the sum of all the exponents. So I can write this as p to the power sigma ji. Sigma ji is nothing but j times product of yi mod p to the power l. Okay. So essentially observe that what have we done over here as a result of this? We have transformed the problem of computing this product modulo p to the power l, xi's can be arbitrarily large, to the problem of computing this product. And what is the thing? So these yi's are actually small now. Okay, so these yi's, observe that they are actually the quotient of this. So basically they are even smaller than this term. Okay, so any quotient is of course smaller than the dividend. Okay, so they are bounded by p to the power l. And now the rest is just making sure we can do this. So yeah, so as I said, so let ai be such that yi is congruent to g to the power ai mod p to the power l. Okay, so here we again just look up the table. So we are given yi, I just look up the table and I find ai over here. We sum all the ai's. So let me just write this over here by table lookup. Next, let a be the sum of all the ai's. Next, what we do is that we do an inverse table lookup. Okay, so now we do a lookup of this table and find out like what is the value for which g to the power, no, so here actually we are looking up this table. Now we look up the previous table. So let p be equal to g to the power. Okay. Now again, these exponents, so we know that they are actually, we only have p to the power l minus p to the power l minus 1 distinct exponent. So I actually just need to do this summation modulo p to the power l minus p to the power l minus 1. Okay, so I can just set a to be that. So it's the same value. It will give me the same value over here. And now we will just compute the following in parallel. Okay. So what we have is, so what do we get here? So if we look at t, what is t equal to? Okay, so we have computed t so far. So t is equal to this g to the power a mod p to the power l. What is g to the power a? G to the power a is sigma g to the power sigma ai. Okay, and anyway the group has order p to the power l minus p to the power l minus 1. So therefore I can just write it as g to the power just sigma ai mod p to the power l. Now what is g to the power sigma? G to the power sigma is product of g to the power g of 1, g of 2 and so on. So what is g to the power ai? A1, g to the power ai is nothing but yi. So I have product of all these yi's mod p to the power l, and product of all the yi's mod p to the power l is nothing but this quantity divided by p to the power j. Okay. So essentially what do I have to output now? If I want to output this, what should I output? Just t times p to the power j, and that's it. Where are you saying?
So like yi is the modulo p to the power l.
Huh.
And so yeah, and here we have the entire g to the power ai into this modulo. So
Where? Here?
Distributing the modulo. Yes.
Yeah, we are redistributing the modulo. Yeah. So what are you saying?
So I was saying this is possible.
Huh?
I was saying this is possible.
No, I am just so this is just for our analysis. So we are not even computing this. Okay, so we compute t, and then in the sixth step, what we will do is that we will just output t times p to the power j modulo p to the power l. That's all. So why this is the correct answer? So this is the analysis. So because t is nothing but product of yi mod p to the power l, and that times p to the power j is this for us. Okay. So what are the steps over here? So let's go through the steps. So here we are doing this in parallel. So as I said that these numbers are small, so therefore I can do this division in NC1. Here I am again computing an iterated addition, that is in NC1. Okay. Here I have already computed the table of the discrete logarithm. So here I am using the anti-logarithm table. Okay. So given yi, I am computing what is the power ai such that yi is congruent to g to the power ai. Okay. And here I am doing the opposite one. Given a, I am computing what g to the power a is. Okay. I am setting that as t, and that's it. So what next? So next we will show is that, so what we have now is that we can compute iterated product modulo a prime power. Next we will show is that how we can actually represent our actual product as a product of So how we can represent the actual iterated product as an iterated product modulo a prime power, okay, how we can actually come to that. So for that what we will need is the okay, so before getting to that, let me just state one more exercise for you, or let me state it as a theorem and you can actually verify the details as a exercise. So this is something that is not difficult to see. So given x and y to n bit integers and m which is less than or equal to m, computing x to the power y mod m is in log uniform NC1. The proof idea is actually just a few things, but I'll just give you some hints to the proof. So what we do is that instead of x, first what we will compute is x mod m. Okay. So first observation is that x to the power y mod m is the same as x bar to the power y mod m, where x bar is equal to x mod m. This we can compute, right? We have seen last class that given an number x and a small number m, I can compute this efficiently. Okay, so I can get x bar efficiently. This is an exercise for you to check. Actually, this is not even an exercise, this is actually quite obvious that x to the power y mod m is equal to x bar y mod m. So we have reduced x to x bar. How can we reduce y? So instead of computing with respect to a large power, can you say that I can write again? So this is point number 1. Point number 2, can you say that x bar to the power y mod m is the same as x bar to some y bar mod m for some y? Can you guess what that y bar should be? Exactly. So it will be the size of that multiplicative group mod m. So the size of that multiplicative group we have already seen. What is it? So it actually basically, well, we haven't seen the size, so it is basically all the numbers that are co-prime to m, right? So I can write this as y mod phi m where phi m is number of elements in z mod mz that are co-prime to m. Okay. So verify this. So 1 and 2, please make sure you verify. 1 is very easy, 2 is a little bit more work, but it is also an easy exercise in group theory. And once you have verified this, essentially what the problem boils down to now is computing x bar to the power y bar, where both these numbers are very. So again observe that phi m is even smaller than m, right? So I am computing a small number to the power another small number mod m, and this actually can even be done by brute force. Okay. So this is easy to do. Okay, so now let's move to the next result.
The y bar is still of the order of n.
It is of the order n, yeah, it is actually less than n, yes. Y bar is less than n. So it has log n bits only now. Y had n bits. So y bar is equal to, is at most phi m is at most m is at most n.
But to do it in log terms, one would have to use something like repeated squaring. I think
Yeah,
you want to-
yeah, you have to do repeated squaring, which is fine because the numbers are small now. So yeah, by brute force I meant repeated squaring only. Do it. So think about it. Okay, actually that is also not very obvious. It is not immediate. So that is also an exercise. Uh, how you can do it, how you can give a NC1 circuit for this now. Okay. Yeah, so I don't think we will be using this result, but this is just, as I said, interesting to observe. Okay. So now, okay, before I give the definition, I have to state the problem. So how do I want to state? Okay, just call it the Chinese remaindering problem. Okay. So what is the problem? So given C1, C2 up to Cn, where each of them are less than n square and pairwise co-prime, and x1 up to xn such that xi is less than ci, compute x such that x is between 0 and product of the ci's and again for all I x mod ci is equal to xi. So let's try to understand this. So what this problem says is that if we are given a set of numbers that are small, in the sense that they are bounded by n square and they are pairwise co-prime. So for any ij, ci, cj are the GCD of ci and cj is equal to 1. Okay, so they are pairwise co-prime. And you are also given another set of n integers such that each xi is at most ci. Okay. Of course, they are, you can assume they are greater than less than ci. Yeah. And okay, let's assume it is strictly less than ci. I mean, I don't think it matters, but okay. Now, given these two set of numbers, we have to compute a number x, okay, such that x is not too large, okay, x is at most the product of these Ci's, and x has the property that if I divide x with Ci, the remainder is equal to Xi. Okay. This should be true for all I. So now the first question is, so what is the first question when one sees a problem like this? That why, I mean, should such an x even exist, or why should such an x exist? Okay. So this brings us to the Chinese remainder theorem. So there is this again a theorem by the same name, which says that if you are given these Ci's and these Xi's which satisfy this property, then there exists a unique x, okay, so there exists an x which is less than this product, and that is the only x which has this property, such that x mod Ci is equal to Xi. Okay. And the theorem is again not very difficult, so you can try. So existence, uniqueness is I think quite easy to prove. Okay, so if you assume there are two such numbers x and y which have this property, you can very easily show that x will be equal to y. Existence is again a little bit more difficult, but it is again very elementary linear algebra. Okay, so using some not linear algebra, but yeah, elementary algebra. So using some elementary algebra, you can show that there exists such an x. So you can actually try proving this by yourself if you are interested, or you can even look up a proof. It is there everywhere. Okay. There exists a unique such x always. Okay. So this is the Chinese remainder theorem. So I leave this as a exercise for you. But here we will assume that this is true, and our task is to compute this x. Okay. So what we will show is that well, we may not always be able to so at this point we might not be able to compute it, but we can actually reduce it to one other problem. So what we will show is the Chinese remaindering problem is NC1 reducible to the problem of computing this product of Ci's. So basically, if someone gives me this product as an oracle, if someone tells me what this product is, the rest I can do it in NC1. Okay, that is basically given all these Xi's and all these Ci's, I can output an x such that x mod Ci is equal to Xi. So the proof is somewhat similar to what we saw earlier. So again, we will basically be operating in this multiplicative ring. So okay, so what we do is, first we are given all these Ci's. So first we compute the product of Ci, so let's call it as C, using my oracle. So this is the only step where I will be using this oracle. Now once I have computed C, the rest is just all NC1 computation. So set Vi as equal to C by Ci. Okay. So what is Vi now? So Vi is basically the product of all the Cj's other than I. Okay. So in other words, therefore, for all j not equal to I, Cj divides Vi and Ci does not divide Vi. Why can we say that Ci does not divide Vi? Cj divides Vi is clear because C is the product of all the other Cj's. Okay, so they must be dividing this. But why can I say that Ci does not divide Vi now? Because because by our initial assumption that all the Ci's are co-prime. So none of the other Cj's has Ci as a factor. Okay. Huh? Why?
Why does not divide Vi?
Uh, why Cj divides Vi? Cj divides Vi because that is how it is defined, right? C is the product of all the Ci's, right? So it must divide. So for now, if I take J to be anything other than I, it must divide, right? And because I have, okay. Now we will compute Wi, which is Vi inverse mod Ci. Okay. So this again, Ci is small for us. Ci is bounded by n square. So this we know how to do it in NC1. We have seen last time. What can we say about this quantity? So what we can say here is that, well, Wi is greater than 0 because it's a remainder, and it is less than Ci, right? And because Wi is equal to Vi inverse mod Ci, Vi Wi is congruent to 1 mod Ci, right? What else can I say over here? I think that's okay for now. I think it's okay, and let us just set this quantity as Ui. Okay, so this product I'll just call it as Ui. Now next step is, so again before going into the next step, what is the value of Ui? Okay, so what is the bound on Ui? So note that Ui, which is equal to Vi Wi, so Vi is nothing but C by Ci, okay, and Wi is at most Ci, okay, so this quantity is, I can write this as at most this, so this is actually at most C, okay, so each Ui is bounded by C for us. So next Okay, that's fine. We compute sigma, let's use J. Xj. Let's give this a name. Y equal to xj uj. Okay. So what can we say about y over here? Now y mod ci is equal to sigma xj uj mod ci. Vj wj mod ci. Now what can you say about this sum? What are all the terms? Okay, so here I mean purposefully I have used a different index j over here because I is the one which is with respect to which I am taking the modulus, and I have all these terms over here. So look at all the terms when j equal to 1, j equal to 2 and so on. What happens when I divide it by ci? Okay. So what is vi over here? Okay, so look at this term vi's. Okay, so I have all these vj's over here. So when j is not equal to I, okay, so for every j that is not equal to I, Cj divides Vi, okay. So what will happen to all those terms? What will happen to the remainder modulo all those terms? They'll all be 0, okay. So because Ci for all j not equal to I, it divides Vj, therefore this is equal to 0. So which is the only term that remains? When j equal to I, and what happens when j equal to I? So when j equal to I will have, well, this will be equal to whatever. So VIWI is congruent to VIWI is congruent to 1, so this will be just Xi mod Ci, right, and that's it. In fact, I don't even have to write this mod over here because I know that all these Xi's are at most Ci, right. So Xi mod Ci is the same as Xi, okay, so I don't even need to write this mod over here. So now what we do is that one more observation. What is the bound on this value? Okay. So y is of course greater than z. What is an upper bound on y? So how many terms are here? There are n terms in this summation. What is the value of each term? So each of these xj's are bounded by Ci. Each of this Ci is bounded by n square. So I have n times n square, and each of the uj's we have proved it is bounded by C, right? Each of the ui's are bounded by C. So it is n cube times C. Now what we do is that in parallel for all t equal to 0 up to n cube minus 1, compute y minus tc okay, and output x as y minus tc such that y minus tc is greater than 0 and less than c. Okay. So y is bounded by this, so I have to go at most till the value of t equal to n cube. Well, okay, n cube, I can go up to n cube also, doesn't matter. I'll have to go at most till the value of t equal to n cube before it becomes negative, and I'll check for each of those values of 2 when is y minus tc between 0 and c, okay. And that is my value of x that I want to output. And we have just shown that if I output this as the value of x, it will satisfy my given criteria. Okay. So why is this? So okay, maybe I can just write this over here. So again, note y minus tc, if I do mod ci, what is this equal to? So all these ci's are product of c is basically the product of all the ci's. So doing modulo ci, this disappears. So this is just congruent, in fact equal to y mod ci, and here I have proven that y mod ci is equal to xi. Okay. So the number x that I am outputting at the end has this desired property. Sorry, not ci, xi. Okay. Okay. So we are all. Which one?
Why it is less? Why is the upper bound n cube?
So this is my y.
So it is.
There are n terms. So I have an n over here. Each xj is bounded by. So each xj is bounded by cj, and each cj is bounded by n square. Right. So that is therefore each x. So each xj is bounded by n square, so therefore I have the n square. Now each uj, we have shown it is bounded by c. So therefore it is n cube times c. In fact, yeah, I can have n cube minus 1 because it is actually strictly bounded by n cube times c. Okay, this is a strict inequality. So it is strictly less than that. So, but it's okay. Okay, so we are almost there, just maybe a little bit more is remaining to complete the proof. We need one more important tool that we will be seeing next time. It is what is called a good modulus sequence, and once we use that tool, we will be able to get our actual problem, that is division in NC1. Okay. So I will stop here today, we will continue next time.